Observational fact. By the early 1930s, distances were estimated to several nearby galaxies, and the expansion of the universe was established. The Milky Way became part of a vast population of galaxies that are illuminated by their stellar populations. In optical images, galaxies appeared to be well separated in space, and the concept of galaxies as isolated regions, island universes, was born, a view that remained in place for decades. After 1950, with the advent of large optical telescopes and new technologies, our model for galaxies grew richer. Radio observations revealed the presence of often billions of solar masses of interstellar gas, as well as showing that some galaxies emitted much of their power at radio wavelengths, a process requiring massive injections of electrons moving at nearly the speed of light. These data and X-ray observations led to the recognition that multi-million solar mass black holes lurk in the centers of most giant galaxies. With the confirmation of the Big Bang model, it was obvious that galaxies had to form in the early universe and then evolve into their present-day structures. However, theoretical models for galaxies consisting only of normal baryonic matter failed to produce credible results. The answer came from an unexpected quarter. In disk galaxies, the rotation speeds at large radii failed to decline as required if galaxies consisted only of visible stars and gas. An extra invisible component, the dark matter halos, evidently surround galaxies and make up most of their mass. Dark matter-dominated models of galaxies not only fit the data but also allowed for the development of a testable theoretical framework for galaxy formation and subsequent evolution. In the late 20th century, the Hubble Space Telescope and ground-based 8 to 10 aperture telescopes opened the way to the study of youthful galaxies. One of astronomy's great advantages is the ability to directly see the distant past, provided, of course, that one has sufficient sensitivity. These studies and their multi-wavelength follow-ons revealed that young galaxies are compact, interactive, and potentially supporting stupendous star formation rates. In other cases, power outputs equivalent to trillions of suns were supplied by young supermassive black holes, as they rapidly grew by accreting gas, and likely also stars. Consistent with the hierarchical growth through mergers concept in dark matter models, galaxies in their youth were anything but the stately island universes of the 19th. So where are we now? We know that galaxies are complex physical systems that experience dramatic evolution as they age, interact with their environments as they convert gas into long-term storage in stars, or sequester normal matter into black holes. The presence of dark matter halos is the standard model, one that we constantly check through comparisons between ever-improving simulations of the development of cosmic structure in an evolving universe and increasingly rich observations. With the power provided by high-performance telescopes operating across much of the electromagnetic spectrum, we now can admire and study the complexity of galaxies in ways that our eyes cannot see, and at the same time enjoy their celestial beauty when resolved into myriads of stars or fantastic structures of interstellar gas. This book introduces the world of galaxies from a 21st century perspective. We have learned a great deal since the existence of galaxies began to be seriously recognized almost exactly 100 years ago, but still have a long journey before we fully understand these natural marvels. Enjoy this guide with its many images of galaxies. And if you have a chance to observe a galaxy through a telescope, most likely as a smudge of light, you will more fully realize why what you are seeing is one of nature's wonders. Ant Colors of the Andromeda Galaxy. Spectacular portrait of the Andromeda Galaxy in its full, vibrant colors, with bluish spiral led with bursts of star formation, and in yellowish population of stars near the central hub. The Milky Way's coming collision with Andromeda. This image shows one moment in the future collision of the Milky Way with the Andromeda Galaxy, which will produce a chaotic supergalaxy, a merger some 4 to 5 billion years from now. Gazing into a summer sky. When I was 14 years old, I was invited to a star party in the little town of Oxford, Ohio, where I grew up. Someone had a 6-inch telescope there, and I was immediately entranced by the realization that I could walk outside into a yard and gaze deeply into the universe. It was Saturn that caught my attention at that first star party, but soon I was out in a large cornfield in the back of my own subdivision, night after night, exploring the sky with a simple pair of 7x binoculars. What a spectacular summer of binocular stargazing that was! I knew almost nothing of the sky and had no telescope. Every new view was a discovery, whether it was scanning along the glistening backdrop of the Milky Way, spotting a star cluster, or coming across a bright and colorful star. I took the first steps in a deep knowledge of the sky that summer, something that too few stargazers now possess, in an era of computerized go-to telescopes. Soon I wandered my binoculars, field of view, into the great square of Pegasus and across the nearby constellation Andromeda. The glow I encountered there, like a bright, hazy star surrounded by an elongated oval fuzz, I soon learned was a pretty special deep sky object. I had stumbled onto the Andromeda Galaxy, and as soon as I learned what it was, I also learned to see it with my eye alone under our dark Ohio sky. In fact, for most people, it is the most distant object visible to the unaided human eyes. The Andromeda Galaxy is a galaxy like our Milky Way, located some 2.5 million light-years away. That's 57 million trillion kilometers, a long hike. Until the early 1920s, no one knew what galaxies were. Moreover, they had no idea how large the universe was. For many decades beforehand, spiral nebulae were thought to be strange gas clouds within our own galaxy. In the early 1920s, American astronomer Edwin Hubble made a breakthrough discovery at Mount Wilson Observatory that led to understanding the fundamental nature of galaxies. Aided by work by Lowell Observatory astronomer Vesto M. Slipher, Hubble and others deciphered the cosmic distance scale, at least to a first approximation. By the late 1920s, astronomers and the informed public understood that we live in a universe filled with galaxies, and that the Milky Way and the Andromeda Galaxy are just two of them. As I learned more and more about galaxies, I turned to every book I could get my hands on. I was immersed in these distant objects right away. A small astronomy club called the Astronomical Association of Oxford, Ohio, was built around chiefly college students in our community, which hosted Miami University in southwestern Ohio. They were looking for a columnist to write about galaxies and other distant objects in the sky, collectively known as deep sky objects, the stuff beyond our solar system. I started writing a column about my observations, and this led to me starting a little magazine, a newsletter really, produced at first on a mimeograph machine in my father's chemistry office at the university. Deep Sky monthly reported on numerous galaxies, and grew over its 5-year lifespan to a circulation of 1,000. This growing interest in observing galaxies coincided with a burgeoning availability of larger telescopes in the hands of amateur astronomers in what became known as the Dobsonian Revolution. John Dobson, a San Francisco area amateur astronomer, pioneered a technique of making large telescopes with inexpensive mirrors, perched on simple mounts that moved up and down and sideways like a battleship gun turret. Larger telescopes in the hands of amateur astronomers meant that more and more people could see fainter and fainter objects for themselves, including numerous galaxies. Interest in observing the sky skyrocketed. One of the books I discovered early on was Galaxies, a pictorial book with a smartly written scientific text by the great science writer Timothy Ferris. Published in 1980, the book contained numerous beautiful photographs and clever diagrams that showed the structure of our Milky Way galaxy and the universe of galaxies around us in a pseudo-3D style. I loved this book, and it was a big influence on me and my early astronomical interests. In 1982, fresh from Miami University, I was hired as an assistant editor of Astronomy Magazine, the world's largest publication on the subject, and went to Milwaukee, bringing my small magazine with me. Retitled Deep Sky, and now a quarterly, the Journal of Observing Galaxies, Clusters, and Nebulae reached a peak circulation of 15,000 during its 10-year lifetime. By 1992, our company decided that I shouldn't spend a quarter of my time on this small magazine, but should put all of my gusto in astronomy. I became Astronomy Magazine's 6th editor-in-chief in 2002, and have enjoyed writing about galaxies in one form or another for 40 years now. I still treasure Timothy Ferris's book as one of my early favorites, but practically everything we know about galaxies has changed in the last 40 years. In the back of my mind, I always thought about an update of this book for the next generation, now describing the barred spiral nature of the Milky Way, our far deeper knowledge of the galaxies around us in the local group, the large-scale structure of clusters and superclusters in the universe, the ubiquitous nature of black holes, and many more topics that we had just hints of 40 years ago. You're the result is what you hold in hand. I invite you to join me in our imaginary spaceship and travel far out into the cosmos to explore an amazing universe that we now know in great detail, and one that 40 years ago could hardly have been imagined. Ghostly glow of the Milky Way-esque of the Milky Way galaxy stretches across night sky and is visible overhead from a dark during the right season and time of night. What EE is the unresolved light from billions of stars aired along our galaxy's disk, as viewed from Ackley What Our Galaxy Looks. Chapter 1. What are galaxies? W. Aves crashed along the beach at Santa Monica. Vast stands of forest speckled the mountains north of the city, and a mesmerizing network of roads crisscrossed here and there. In 1923, Los Angeles had a population of 1 million, just 1/4 of its present size, and the city was in the midst of explosive growth. At the California Institute of Technology, an American physicist, Robert Millikan, won the Nobel Prize in Physics for his measurement of the charge carried by a single proton or electron, and for work on the photoelectric effect, including his observation that many metals emit electrons when they are struck by light. Amelia Earhart took periodic flying lessons in the area. The Hollywood Bowl had recently opened for concert. Fast fact, Galaxies are vast collections of stars, gas, and dust, ensconced in dark matter halos that are the basic, large-scale building blocks of the cosmos. There are numerous types of galaxies in the universe. Performances. And a young cartoonist named Walt Disney arrived in town with $40 in his pocket. Despite the area's forward-looking involvement in science and technology, it was a primitive time. No one yet knew the size and scope of the universe. People had looked at the brightest galaxies in the sky, the fuzzy patches in Andromeda and the Magellanic Clouds in the southern hemisphere, but no one yet understood exactly what they were. One big question floated out there. How big is eternity? Is creation limitless? Soon Los Angeles would play a pivotal role in defining the distance scale of the universe. One big question floated out there. How big is eternity? Is creation limitless? The 100% telescope. On October 4, 2003, in the midst of this peculiar Western paradise, a brash young astronomer left his Pasadena house and trekked up to the Mount Wilson Observatory, not far from Los Angeles itself, to the 100-inch Hooker telescope, at the time the largest telescope in the world. Originally from Missouri, Edwin Powell Hubble had moved to Illinois, graduated from the University of Chicago, and then earned a master's degree as a Rhodes Scholar at Oxford University. He embarked on a career in astronomy only after returning to school at the age of 25 to pursue a Ph.D. Hubble was now in his fourth year as a staff astronomer at Mount Wilson. He relished using the 100-inch Hooker telescope to study his favorite subject, the fuzzy nebulae, mysterious, glowing gas clouds that appear scattered across the sky. No one fully understood these nebulae, although they were suspected to be the birthplaces of stars. The adventurous amateur astronomer William Parsons, 3rd Earl of Rosse, had first sketched nebulae with spiral structures that looked like faintly glowing whirlpool patterns, using his mammoth telescope in rural Ireland in the mid-19th century. But even nearly a century later, little more was known about them. Hubble was interested in cracking the code of nebulae, particularly spiral nebulae. His Ph.D. work had centered on the topic. These nebulae's spiral shapes suggested that they are rotating, but otherwise they mystified Hubble and other astronomers. Var, in 1923. The photographic plate that defined galaxies on October 5, 1923, astronomer Edwin Hubble made an exposure of the Andromeda Nebula with the 100-inch Hooker telescope at Mount Wilson Observatory near Los Angeles. He was initially excited, believing he recorded a nova, an exploding star, after analyzing the plate. He marked the star with an N, and it lies between two tick marks he drew on the glass plate. The famous plate, designated H335H, would help to unlock one of the universe's biggest secrets. A short time later, Hubble realized he had not seen a nova, but a variable star of a particular type called a Cepheid, with very well-known characteristics. Because their absolute magnitudes and light curves were well known, astronomers could use Cepheids to determine distance to them. Astonished, Hubble found that the Andromeda Nebula was actually a distant galaxy, perhaps 1 million light-years away, far larger than astronomers believed the entire universe was at the time. Also, with this plate, he unlocked the nature of galaxies. This plate and an enlargement show the nuclear region of the Andromeda Galaxy on the plate's upper right corner, with the famous notation, the N for nova crossed out, and Hubble's exclamation, in red ink var. 380. Avar, N 6 October 1923 on the night of October 4th, 1923. Hubble used the 100-inch Hooker telescope to take a 40-minute exposure of one of his favorite nebulae, the Great Nebula in the Andromeda constellation. This spiral-shaped cloud was large, bright, and faintly visible to the naked eye as a fuzzy smear of light for those located away from the city lights of Los Angeles. The night had very poor seeing when he took the exposure, because Earth's atmosphere was relatively turbulent that night, and so the star images were not perfectly small dots. Nevertheless, Hubble's examination of the photographic plate he had made revealed a suspected nova, an exploding star. It was exciting to record such a relatively rare event inside one of the spiral nebulae. Hubble photographed the Andromeda Nebula again the next night, hoping for a better quality image of the suspected nova. The resulting photographic glass plate, exposed the night of October 5 to 6 and designated H335H, would become one of the most celebrated in all of scientific history. On it, Hubble successfully recorded the nova again. But before he could analyze it further, his periodic observing run on the 100-inch telescope ended, and he had to leave to accommodate other observers. Early in the morning, he left the mountain and returned to Pasadena. At his office down in Pasadena, away from the mountaintop observatory, he continued studying earlier images of the Andromeda Nebula region taken by others. And then he made an unusual discovery. A nova brightens dramatically and then fades into oblivion, but the star he recorded appeared on older plates, brightening and fading regularly over a period of 31 days. This star was not a nova then. It had to be some other kind of star inside the Andromeda Nebula. Hubble's breakthrough. Suddenly, Hubble came upon the solution. He realized that he had made an image of a type of star similar to a well-known one in the constellation Cepheus. On his photographic plate H335H, he crossed out N for nova and wrote var, denoting a variable star. Moreover, this star was a special type of variable that brightened and faded in a precise way. Astronomers had long studied this kind of star, which came to be known as a Cepheid variable, and they knew how intrinsically bright it was. By knowing how bright the star really was and measuring how bright it appeared to be in the sky, Hubble could use the star as a guidepost to gauge the distance to it. With his photographic plate, Edwin Hubble had single-handedly reset the size of the cosmos. This was a monumental realization. Hubble calculated that, owing to the star's faint light, it must lie 1,000,000 light-years away, and so must the entire nebula that surrounds it. This meant that the universe stretches across a distance at least 3 times larger than most astronomers then believed. With his photographic plate, Edwin Hubble had single-handedly reset the size of the cosmos. How to view galaxies from your backyard. Soon after Hubble's discovery, astronomers frantically began to collect data on many of the brighter objects in the sky that were suspected of being distant galaxies. These included many of the bright galaxies we can see in our sky today, which can be observed with small telescopes. Here's how to see galaxies in your sky. Choose a moonless night. You want maximum sky darkness, a clear sky, and an observing site as far away from cities and other light sources as you can get. Use a 4-inch or 6-inch telescope. This is the minimum size, but an 8-inch or 10-inch telescope is even better, so that you can collect the maximum amount of faint light. Choose the right timing. The Milky Way is prominent in the summer and winter evening skies, so in spring and autumn other well-known galaxies are unblocked and can be viewed with a backyard telescope. These include the beautiful spiral galaxy M81 and its neighbor M82 in Ursa Major, the Whirlpool galaxy in Canes Venatici, M101 in Ursa Major, the Black Eye Galaxy in Coma Berenices, the Sombrero Galaxy in Virgo, and the Southern Pinwheel Galaxy in Hydra. Discovering the galaxies. Hubble's discovery set off a firestorm of activity among astronomers researching other spiral nebulae. Countless observations followed, and follow-up studies rolled on for many months as bickering and soul-searching lit up the world of professional astronomy. Adding fuel to the fire was a debate staged several years earlier, in 1920, between two prominent astronomers of the day, Harlow Shapley of Princeton University and Heber Curtis of the Allegheny Observatory. Shapley believed that the Milky Way galaxy constitutes the entire universe, while Curtis speculated that spiral nebulae are separate galaxies from the Milky Way galaxy, essentially island universes. Though not everyone would concede it yet, Hubble's discovery seemed to prove that Curtis was right. Hubble continued imaging Cepheid variables in other spiral nebulae, such as M33 and Triangulum, demonstrating that they, like Andromeda, are so far away that they must be distant galaxies. Hubble's observations indicated that galaxies are the basic units of stars, gas, and dust in the universe, and that they exist on a fantastic scale. He had many doubters, chief among them Shapley, but Hubble pushed on. The findings of the confident 35-year-old were subsequently splashed onto the front page of the New York Times by November 1924. Egged on by supporters, he sent a paper summarizing the results to be read at the winter meeting of the American Astronomical Society, the professional organization of astronomers, on New Year's Day, 1925.
After the distinguished Professor Henry Norris Russell of Princeton University read the paper aloud at the gathering, galaxies were on their way to becoming widely accepted. Fast fact, the galaxy we live in is called the Milky Way, and it contains some 400 billion stars, one of which is the Sun. Hubble's observations indicated that galaxies are the basic units of stars, gas, and dust in the universe, and that they exist on a fantastic scale. A breakthrough with galaxy colors. Several more years led to another huge advancement. A galaxy's spectrum is a picture of the collected light from all of its stars and gas. In 1929, Hubble and other astronomers recorded many spectra of galaxies and noticed that they appeared to be shifted toward the red end of the spectrum, increasing the wavelength and lowering the frequency of their light. This was an effect first noticed years earlier, in 1912, by Vesto M. Slipher, an astronomer at the Lowell Observatory in Arizona. You experience this effect, called a Doppler shift, with sound every time an ambulance with its loud siren passes you. As it approaches, the siren seems high-pitched, and when it passes and heads away from you, the pitch drops lower, increasing the wavelength. Galaxies similar to the Milky Way Hubble Space Telescope, SDS, and lowering the frequency of sound. The same thing happens with light.
When objects are moving toward us, the frequency of their light shifts higher, toward the blue end of the spectrum. When they are moving away from us, their light shifts lower, toward the red end of the spectrum. Consequently, the red shift of the spectra of distant galaxies indicates that the galaxies are moving away from us. And this means that the universe is not only immensely bigger than previously thought, but also that it is expanding to become even bigger as time marches on. Here comes the Big Bang. Hubble's work, building on the earlier studies of Slipher and the astronomer Milton Humason, showed that, generally speaking, all galaxies are moving away from each other over time. Hubble also found that redshifts can be used to calculate distances to galaxies. This research led to a monumental realization. In 1929, Hubble, with a helpful assist from the Belgian astronomer Georges Lemaitre, suggested that the new data he collected about galaxies supported the theory that if traced backward in time, the paths of all of the galaxies led to a small, dense point at which the whole universe began a Big Bang billions of years ago. This Big Bang commenced the expansion that is causing all galaxies to move apart from one another more quickly in space. The whole universe seems to be flying apart. Hubble analyzed 46 galaxies and proposed what came to be known as the Hubble constant, the rate of expansion of the cosmos. He fixed this number as 500 kilometers per second per megaparsec of space, a higher value than what we know is correct today. Opposite a scrapbook picture of galaxies' early years with the majestic Hubble Space Telescope, astronomers studied 400 galaxies, similar to the Milky Way, and created a picture of how our galaxy built up over time. They believe the galaxy began as a low-mass, bluish aggregation of gas with old stars that evolved into a flat disk with a central bulge, and later the barred spiral galaxy we know today. Hubble and the expanding universe. Hubble's credibility skyrocketed following the determination of an expanding universe. This was big stuff. Hubble had piled on lots of supporting evidence for the ideas of the great physicist Albert Einstein, who had proposed in the previous generation that time and space are expanding and that the cosmos is almost unimaginably large. By the late 1930s, following Hubble's big discoveries, it was becoming clear just how significant galaxies are to the story of the cosmos. Astronomers knew that most of the immensely large universe is filled with darkness. Little matter exists outside the island galaxies, which contain all the bright stuff, the normal matter stars, gas, dust, and planets. The universe is like a vast and stormy sea, with little ships' galaxies. Floating on it, and a virtually limitless ocean of utter darkness and foreboding void in between them. Classifying galaxies. By this time, Hubble understood the broad types of galaxies, which he classified in a tuning fork diagram. There are spiral galaxies, like Andromeda, and barred spirals, which are similar to spiral galaxies, but contain a rectangular bar of mate rille through their centers. There are ellipticals, spherical masses of stars, gas, and dust. There are lenticulars, which appear lens-shaped, and there are irregulars, relatively formless clouds of matter lacking organized structure. In the late 1930s, astronomers discovered examples of a new class, dwarf spheroidal galaxies, and later still, astronomers found so-called peculiar galaxies, which seem highly distorted. By the end of the 1950s, they had devised an improved way to classify galaxies based on the research of the French astronomer Gérard de Vaucouleurs of the University of Texas. Fast fact, some galaxies are CL using their character or behaviors. For X interacting or Me galaxies are PA groups of galaxy are intertwined cosmic DAN. CB-ADF examples of all these types of galaxies can be viewed with a telescope from a dark sky site. They include: fast fact, there are several types of special galaxies. Highly distorted objects are often classified as peculiar galaxies. Intermediate, lens-shaped galaxies between spirals and ellipticals are termed lenticular galaxies. Dwarf spheroidal galaxies, the most numerous, are a subset of ellipticals. Spiral galaxies, the Sunflower Galaxy, IC 342, and NGC 1232. Barred spiral galaxies, NGC 1300, NGC 1512, NGC 1530, NGC 4921, and NGC 5701. Elliptical galaxies, M49, M87, and NGC 1052. Lenticular galaxies, M84, NGC 2787, and NGC 4111. Irregular galaxies, NGC 1569, NGC 3239, and NGC 4214. Peculiar galaxies, ARP 81, ARP 220, Centaurus A, Fornax A, M82, and Perseus A. de Vaucouleurs' classification scheme was more complex, forming a 3D cosmic lemon that accounted for more properties of the basic types of galaxies. For spiral galaxies, this included further details on bars, notes on whether a galaxy showed rings of encircling material, and notes on how tightly or loosely wound the arms of a spiral galaxy appeared to be. De Vaucouleurs also cataloged details about irregular galaxies and described peculiar galaxies, which had experienced galactic train wrecks, interactions with nearby galaxies that warped their shapes. How astronomers classify galaxies. Astronomers have struggled to classify galaxies since the 1920s, when Edwin Hubble at California's Mount Wilson Observatory first proved that they were island universes beyond our Milky Way. Hubble found that he could lump most galaxies into a few broad types: elliptical, normal spiral, and barred spiral, and he placed them into a tuning fork-shaped sequence. Galaxies display a huge range of sizes and masses, from nearby dwarfs that contain fewer stars than a globular cluster elliptical galaxies to mammoths like M87. Galaxies show a range of structures too, including bulges, disks, bars, rings, and spiral arms. The subtler details of galactic structure required a more nuanced scheme than Hubble's. In the late 1950s, Gérard de Vaucouleurs devised a 3D version of the tuning fork shown opposite, based on observations of a few hundred southern galaxies. But distant galaxies, seen when the universe was younger, smaller, and more crowded, don't fit into the scheme. Moreover, new surveys of tens of thousands of galaxies suggest they occupied two distinct zones when plotted by color and brightness. No one yet knows how to reconcile such observations with the smooth variations astronomers see among different galaxy types. Study the accompanying diagram carefully. Giving Hubble's tuning fork a half-twist creates the lemon-shaped classification volume Gerard de Vaucouleurs developed beginning in the late 1950s. Normal galaxies occupy the top half. Barred galaxies go on the bottom. Different galaxy types occur left to right. Codes describe each galaxy based on its position within the volume. The lemon's height reflects the relative number of each galaxy type found in the sample. Barred spiral GA. Fast fact, elliptical galaxies appear as ellipses from our point of view. They are really often spherical or football-shaped and consist of a great cloud of stars and gas, often floating within halos of globular clusters with a massive dark matter halo on the outside. A normal, shaped M87 elliptical, EO or LNGC 3115 lenticular, so normal plus M33 spiral, SACD-NGC, SA-SHE 106b S-shaped the Milky Way, barred the Pinwheel Galaxy C. Say B barred. The incredible scope of the cosmos. For years, something like 100 billion galaxies exist. Studies show the total number of galaxies have merged over time. We are 100 billion verse have merged over time, creating a SM rent number like 100 billion. We are hanging out in just one of them, the Eye. Fast fact, the most familiar type of galaxy, a spiral galaxy, has spiral arms that wind around the galaxy's center in a glowing disk. The spiral arms are created by density waves, ridges that are denser than the areas surrounding them. They contain a disk of stars and gas, a central hub or bulge packed with stars and gas, a large halo of globular star clusters, and an outer halo of dark matter. These basic structures of the cosmos, like ships an ocean of vast darkness, give us a glimpse B world to understand the meaning of why we're H. As astronomers have discovered more and axes since the 1920s, they have acquired one mental piece of knowledge. The universe is really imagined that you could climb into a spaceship out into the universe, seeing more and more DS as you went on. Let's also imagine that the space travel at the speed of light, the fastest speed in the cosmos. That's about 186,000 miles per speed at which photons, particles of light, are St. Eyes, enabling you to read this book. Galaxies, the basic structures of the traveling to the galaxies. In our spaceship, let's set out from the Milky Way galaxy, our home. The closest galaxy we can encounter is the Sagittarius Dwarf Spheroidal Galaxy, a tiny galaxy that orbits ours. If we move at the speed of light, it would take us 70,000 years to reach this galaxy. Another way of thinking about these enormous distances is to understand how long the light we see from other galaxies now has been traveling through space to reach us. The light from the Sagittarius Dwarf Spheroidal Galaxy has traveled since humans made their earliest bits of art inside caves in South Africa. If we traveled for 163,000 years in our spaceship, we could arrive at the Large Magellanic Cloud, our galaxy's largest satellite. Traveling for 200,000 years would carry us to the Small Magellanic Cloud, another satellite of our Milky Way. The light you see from this galaxy tonight has traveled through space since our earliest human ancestors closely linked to our species walked the African plains. Fast fact, clusters of galaxies are collections of galaxies held together by common gravity. They contain a dozen or more large spirals or ellipticals, and possibly hundreds of smaller galaxies. Galaxy clusters typically span several tens of millions of light-years. Cite the weird Barge Spiral 4921. Barge Spiral Galaxy, NGC 4921 in Berenices, is a distant object at million light-years. It is a so-called Mike galaxy, labeled as such by Dean astronomer Sidney Van Den, because it has a very low rate of formation. Its lovely spiral pattern D, the small central bar, gives it the appearance of a delicate painting. He elegant face-on barred L galaxy, NGC 5701 gives us a view of a barred mat is fairly similar to the Milky Ing, at a distance of 77 million Rs in the constellation Virgo. Infant star clusters ring Laxi NGC 1512. Pyro Galaxy NGC 1512 lies million light-years away in the constellation Horologium. Its yellow-colored disk is ringed by of bluish infant star clusters, and a bar that is too faint to be seen. Hers believe the bar funnels the outer ring, leading to the star formation. The Magellanic Bridge, SMC previous elliptical orbit Milky Way, LMC current parabolic orbit 500,000 light-years. Light-years. Taurus local Orlan Arm Sun Perseus Cloud. Sun South Coalsack Milky Way Ophiuchus Chamaeleon Galilupu.